Hi all, welcome to my channel. This is E. Manjula, lecturer in electrical, GIOE, Secunderabad. So from today we are going to discuss about the network analysis and the theorems and how they have been the theorem statements and where it is applicable. So all these things we will see. Okay, so today's session is we are going to see the superposition theorem and a problem which is explaining the theorem statement. Okay, so today's objectives are that state we will state the superposition theorem and explanation about the superposition theorem and application of superposition theorem to networks. So known to unknown. So here we have already discussed about the Ohm's law and KVL, KCL also. Here we will see that the Ohm's law provides only the fundamental tools for solving electrical networks, but it has some limitations. So we know that already that Ohm's law have some limitations. Okay, only for the fundamental networks only it is used, and it cannot be applied to the circuits where more than one source is acting simultaneously. So where if there is two sources, three sources, more than one source, so this Ohm's law cannot be used, cannot be applied. In such cases, we will apply KVL and KCL. So we have solved even problems on KVL and KCL also. So in that cases, we can use KVL and KCL. Then when we can use this superposition theorem, we will see. Okay. So even while applying KVL and KCL to the networks, the number of simultaneous equations. See here the simultaneous equations are increasing. Okay. So the number of simultaneous equations to be handled become more when the network is complicated. So this leads to error in result. We might have directly solving the equation by using KVL and KCL, but it will lead to some errors. The answers which are resulting may not be correct. So for very complicated and where more than one source is used at that position, at that time, we will use the superposition theorem. Okay. So in such cases, we can apply superposition theorem. So here, superposition theorem statement. Okay. It states that in a network of linear resistance containing more than one source of EMF and the current which flows at any point is the sum of all the currents which would flow at that point if each source were considered separately and all other sources were replaced by their internal resistance. So here, while applying, we will apply this theorem where we will see the network which have two or more sources, voltage sources, okay, or current sources also we can use. So here, and we are using, for example, if a network has two sources, we are using one source and making the other source is replaced by something. Okay, we will see how it is being applicable, this theorem, how it is being applicable, but make sure that you should remember that this theorem is applicable when there is two or more sources are available in a network and we have to solve that network. Okay, here, see, internal resistance of an ideal voltage source is 0. Okay, that is a short can be put. Okay. So when we take a network, when there is an ideal source in a network, then we can remove that network, that source, and we can replace it with a short circuit. Okay. Likewise, an internal resistance of an ideal current source is infinite. That is, an open circuit can be put. So here, when there is an ideal current source in a network, we will replace that source with an open circuit, which means it is a infinite resistance. Okay, fine. Uh, there is no ideal sources in a network. Say, if the given sources are non-ideal, then we can replace with their internal resistance. So if it is not ideal, then we can replace the internal resistance which the sources have. Okay. So here the explanation why taking on a circuit. Okay. So which you can easily understand the theorem by knowing this. After completion of this explanation, I hope you will get clearly understand how this theorem is applicable to a network and how we will solve the network. Okay. So here we are considering, say in figure 1, two sources are there. EMF sources, that here are the batteries. Okay. So the battery 1 is 28 volts and the battery 2 is 7 volts. And R1, R2, R3, three resistors. R1 is 4 ohms, R2 is 2 ohms, and R3 is 1 ohm. So here, now we have to solve a network like how the resistance we have to. We have to. So here, we have to know that what is the current flowing through the R1 and R2 and R3. So by seeing this network, we cannot identify how much current is flowing through R2 and how much current is flowing through R1. Okay. So here we will apply a superposition theorem. We will check how it works. Okay. So let us apply superposition theorem to the circuit shown in figure 2. Here, what we are doing, we have battery 1 and battery 2. So what the statement is telling that you have to replace a EMF source. Okay, when there is two source, one EMF source need to be replaced with their internal resistance. Okay, so here the first consider that battery B1 is acting alone in a circuit as shown in figure. So battery 2 is taken out. Okay, therefore other battery B2 is replaced with short. Okay, so here battery B2 is replaced. There is no internal resistance, hence we directly shorted here. So this is a network. So now we have to calculate what is the total resistance. So it will be very easy to calculate the total resistance once it is shorted. Okay. So we can analyze it. So these two, if we analyze these R2 and R3 resistors are parallel to each other. So we can calculate the resistance at this area. And yes, after calculating the resistance here, we can calculate the total resistance. The resistance found here will be in series with R1, so total resistance we can easily found out. Okay, fine. So here, so as B2 is removed, we can calculate the resistance as seen by the battery as. Okay, from the battery side, if we see, So total resistance R is equals to, this is 4 plus parallel. Okay. So 2 into 1 divided by 3, which is equals to total resistance is 4.667 ohms. So now we can find out the current. So the current supplied by the battery V1 as I is equals to 28 divided by 4.6676 amps. Okay, divided by 4.667, which is equals to 6 amps. So the current will flow like this. Okay, the direction what I am showing is a conventional direction. Okay, this is only mostly used direction. So we have not found yet what is the amount of current is flowing in this direction. But we know from this it is flowing 6 amps. Okay, so only one path is there. So we know from R1 is also 6 amps. Okay, so here the direction of actual current flow considered rather than the conventional flow. So rather than the conventional flow, they have considered the actual current flow. So actual current flow is always from negative to positive. The conventional current flow is from positive to negative. Okay. So why it is from negative to positive? We know that electrons will pass from negative to positive. Okay. So the current will also flow from negative to positive, but for conventional, we will use the direction of the current is always from positive to negative. But here the direction is given is actual one. Okay. So from this resistance, it is 6 amps. We have discussed before. Okay. So we can find out the what is the voltage drop across this resistance. Okay. So this is 4 ohms resistance. So 4 ohms resistance. So 4 into 6. So we can find out the voltage drop. Example V1 is equals to I. That is the total right here. I can say even I1 also because I is equals to I1 here present into R1. So this is according to Ohm's law. We know that already. Okay, this is 6 amps into 4 ohms. So which is giving 24 volts. Okay. So the drop across the R1 is 24 volts. So here the resistance R2. The resistance R2 is 2 ohms and the resistance R3 is 1 ohm. So this is 2 ohms and this is 1 ohm. So we have to find out the current. What is the current flowing through this part and what is the current flowing through this part. So how we will find out the currents across these two? By using the currents through various parallel paths can be easily be obtained by applying the current division rule. Okay, so now I will show even that also for easily understanding. So say this is okay, here example for finding out the resistance to R3, the formula is, say now we are, this is a total resistance, so I1 is a total resistance here. And now I want to find out the current which is flowing through R3. So opposite component R2 divided by R2 plus R3. Okay, now this is giving the current I3. I3 is the current which is flowing through R3. Okay, so what is I1? I1 is the current 6 amps into what is R2? R2 is 2 ohms. Okay, this is 2 ohms and this is 1 ohm. Okay, so 2 divided by 1 plus 2, 3. So here get cancel and you'll get 4. So the current to I3 which is flowing is 4 amps. Okay, you can see. So this is 4 amps. Likewise, we have to calculate the current which is flowing through I2. That is equals to 6 into, directly I'm putting the values, 1 divided by 3. Okay, 1 is the resistance of R3. Okay, so here you will get directly that is 2 amps, which is the I2 current. Okay, so this is by a current division rule. Okay, so now we got 2 amps. So likewise, so the total amperes is 4 plus 2 is 6 amps. It should be tallied. Okay, while we have to verify it. So yes, now we have to calculate the voltage across R2. So what is the voltage across R2? The voltage drop in the R2 is that, so V2 is equals to, so once we start applying any theorem or any law to a network, it is very easy for us to find out each and every value at any node. Okay, so we have to remember all the laws and theorems what we are studying step by step, like Ohm's law, Kirchhoff current laws, Kirchhoff voltage laws, Thevenin's theorem. We will see in the next session. Okay, superposition theorem. If you are able to understand all the laws and theorems, you can solve any type of network. Any given network can be solved by you if you are aware of all these theorems and laws. So voltage is equals to I into R. Okay, according to Ohm's law, I into R. So R is here. So into 2. So both are 2, 2. So it is 4 volts. Okay. So yes, it is 4 volts. And now for finding out the voltage across R3, that is, we know that V is equals to I into R. I is here 4 amps. 4 into 1 ohm. So it is again 4 volts. Okay, so we got even this, we got this, yes, everything we got. Okay, now these two are in parallel, so the both the voltage has been tallied, right? We have to cross check even the total voltage. Okay, so this is 24 volts. So 24 volts plus the parallel voltage, that is 4 volts. Both are in parallel, so we will consider only one. So 24 plus 4, 28 volts. So this is also tallied. The next, this is not completed the total superposition theorem. See, we have taken out one of the battery and we are solving this. And now we have to take the now the V1 battery, and now we have to include the V2 battery and now solve the same similar pattern session. Okay, fine. Here, I'm explaining you very clearly step by step. So voltage acting across each resistors can also be calculated. We calculated it. Now, now let's consider that battery 2 is acting alone. So we have to put the battery 2. Now only battery 2 is alone. Battery 1 is replaced by short. Okay, so replace the battery 1 with an internal resistance that is short. So here we know the resistance R3 is 1 ohm, R1 is 4 ohm and R2 is 2 ohm. In the same way how we have calculated previous, likewise we will calculate even this part. So as B1 is removed, we can calculate the resistance as seen by the battery side. From the battery side, if we observe that R1 and R2 are in parallel and these two are in series with R3. So the total resistance is R, which is equals to 1 plus 2 into 4 divided by 6, which is equals to 2.33 ohms. That is the total resistance. So now calculate the total current. So the total current I is equals to V by R. So V is 7 volts and R is 2.33 ohms, which is equals to 3 amps. So the total current which is coming from this is, so conventional direction, here it is a 3 amps. Okay, but now we are using an actual direction. Dear students, do not confuse it. Generally we will use only the conventional direction only. Okay, but here in this problem we have used the actual direction. Okay, so this 3 amps current divides into two parts as shown in the figure. So the actual direction is from negative to positive, so the 3 amps will flow like this. It will divide here and again it will rejoin here. Okay, so the current 3 amps is flowing here. The current through various parallel paths can easily be obtained by applying the current division rule. Okay, so here we have to find out the current division rule again. Okay, so what might be the current flowing through this and this? So that we can calculate here. What is R1 ohm? R1 resistance. R1 resistance is 4 ohms. So this is 4 ohms and this is 1 ohm and this is 2 ohms. Okay, so before when we consider the B1 battery, we have calculate the current division. With the same process we have to calculate the current flowing through R2 and R1. Okay, so if for example the current flowing through say R1 is, so the total current 3 amps into, so we are calculating to R1. So we will consider the R2, that is 2 ohms divided by 4 plus 2, 6. Okay. So 6 and 6 will get cancelled, will get 1 amp. Okay. So 1 amp is flowing through R1. Yes, 1 amp is flowing through R1. Now from R2 is the total current R3 into 1 divided by 6. Sorry, 4 divided by 6. So this is the R1 resistance 4 divided by total resistance 6. Okay. So what you'll get? You'll get 2 ohms. Sorry, 2 amps. Okay. So the current from R2 resistance is 2 amps. Okay, both are tallied. So when we combined the R1 resistance and R1 current and R2 current, both are tallying with the total current. Yes, so 2 plus 1 is 3 amps. Okay. Now we have to calculate what is the voltage drop across the each resistance. So the formula is equals to V is equals to I into R. So from each resistance we know the current what is flowing through the each resistance. So directly we can calculate. So 4 into 1, 4 volts. So 2 into 2, 4 volts. So here 3 into 1, 3 volts. Okay. So these two are parallel. So both are of same voltages. That is 4 volts and 4 volts. So what is the total voltage is 7 volts. So how we are getting the 7 volts? This 4 volts because these two are parallel. So we will consider only one. Okay. So 4 volts and 3 volts. So 4 plus 3 is 7 volts. Okay. Even this is also we got final. So current through various parallel paths can easily be obtained by applying current division rule. Yes. Voltage acting across each resistor can also be calculated. So we have done that part also. So here now we have to superimpose the result obtained, that is add each value algebraically. So now we got by only considering one battery B1 and also the values by only considering B2, that is alone B2. Now we have to superimpose both. So how we will do that? Here this is 28 and this is 7. Okay. So what is the current R1? The current which is flowing from R1. So here the current R1 is 1 amp in. You observe the direction is to right side. Okay. Likewise, we will consider here. This is 6 amps to left side. So both are in opposite direction. So the total current is 6 minus 1 amp. So we will get 5 amps in the same direction as 6 amps. Okay. Yes. Okay. 5 amps the same direction as 6 amps. Okay. Means that so you could able to Understand, I guess. Okay. So what is the total current in R3 and the total current in R2? So we will see even that. So here R3 is 3 amps, here R2 is 2 amps. This is from left side and this is upwards. Okay. First we will see only the one current, say it is R2, that is upwards 2 amps. So here R2 is again 2 amps upwards, so 2 and 2 4 amps. Okay, both are in same direction. And here it is 3 amps this side and 4 amps this side, so the 1 amp will be the final side. Okay, so this is 4 amps. Okay, 4 amps finally, and this is 1 amp to this side. Okay, so this is a total current direction after superimposing both the networks. Okay, finally, so we can found out what is the voltage drop here. Okay, what is the resistance here? Resistance should be always written so that it will be easily for us. Okay, this is 1 ohm. This is 4 ohm. And this is 2 ohm. Okay, so 1 into 1, 1 volt. What is that? I into R. Okay, I into R. 5 into 4, 20 volts. 4 into 2, 8 volts. So we could able to find out what is the voltage drop in each resistance. Okay. So here this shows the voltage acting across various elements. The figure 7 is showing the currents. Okay. So this theorem is applying is so easy and step-by-step process. After superimposing, we could able to know what is an actual values which are passing through the resistance, and we could able to find out the voltage across the each resistance when two resistors are when two when two resistors are connected in when two EMFs are connected simultaneously. Okay. So this is how we have to calculate that we have to apply a superposition theorem to any network. Okay, if there is if there is even a three EMF sources also, we can do the same process. Okay, or many, two or more, we can apply the same. So we have to calculate one by one, and we have to superimpose, and we can get a final value. So applications of superposition theorem is that, please note that while superimposing the result, we have to consider the directions. Yes, always the important that we have to consider the directions. If currents due to all sources are acting in same direction, we can simply add them. If they are opposite to each other, we have to subtract them. Okay. The same rule applies to voltages also, voltages acting across the resistors. So the summary is that we have discussed about the statement of superposition theorem and the explanation of the superposition theorem and application of the superposition theorem and its networks. Hope you have understood the application of the superposition theorem and what is a superposition theorem and when it will be used, the superposition theorem. Okay, one point I would like to tell you that we have calculated here the voltages directly 5 into 4 like that. Okay, but we have calculated the voltage drops in the previous when we considered B1 and B2 separately. Okay, So directly you can add or subtract by taking the values. How we have done for the amperes, you can do the drops also. Okay, and you can do even this method. So there are so many methods to solve the networks. Networks are very interesting when you know all laws and the theorems and the logics. Okay, and yes, if you practice more the networks, it will be very easy to you, and you can easily get the values also. Okay, so hope you have understood today's session. We will see one quiz, that is, what is the internal resistance of an ideal voltage source? It is 0. Okay, that is why we are shorting it. Okay, so while considering one source, other source should be replaced with their internal resistance. Okay, so thank you, Ma. Thank you for listening to my session. So we will meet in the next session with the Thevenin's theorem. Thank you so much.
I'm going to solve some examples using the principle of superposition. To analyze using superposition, we need to follow three main steps. 1. Set all sources equal to 0 except 1 and solve for that source. 2. Repeat step 1 for all sources. And 3. Add the solutions obtained from each of the sources. Example 1. Determine the current I in the circuit using the principle of superposition. At the beginning, we are going to set the current source equal to 0, and we obtain this circuit diagram. The current source is set to 0 by replacing it with an open circuit. Now we just need to find the current I that results from only this voltage source. And we can obtain that by simply dividing 12 by the sum of these three resistances. Since this current is related to the voltage source only, we added this symbol to distinguish this current from the current that results from the current source in the next step. In this step, we set the voltage source equal to 0 by replacing it with a short circuit. And now we just need to find the current, I, that results from only the current source, using the current divider rule, as we can see here. The direction of the current that results from the current source is upwards, which is opposite to the direction of the current that results from the voltage source. And that's why we added this minus sign here to the value of the current that results from the current source, because the direction is opposite. And this current here is the current that results from both the voltage and the current sources. Example 2. Use superposition theorem to find the current I in the circuit shown. Similarly, we are going to set the voltage source equal to 0 and the 40 ampere source equal to 0, and we'll just calculate for this source. So this is the voltage source, short circuit, and this is the current source, open circuit. Now we just need to find the current, I, that results from the 120 amperes source. And we can simply find that using the current divider rule, and we get 30 amperes, the value of the current, I, that results from this current source. Notice that the direction of this current is to the right. Now we're going to solve using only this current source. And again, using the current divider rule, we get the value of the current, which is 30 amperes. Notice that the direction of the current is to the left, which is opposite to the previous current. And now we're going to set the two current sources equal to 0, open circuits, and solve only for the 10 volts voltage source. We can simply find the current by dividing 10 by 150 plus 50, which is 200. The direction of the current is also to the left. Since the direction of the current that results from these two sources is to the left, we add them here, whereas the direction of the first current was to the right, which is opposite to the direction of these two currents, and that's why we put a minus here. And this is the final solution for this example. Example 3. Use the superposition theorem to find V in this circuit. In the same way, first of all, we are going to set this source equal to 0, so it's replaced by open circuit, and we just need to find the voltage V using voltage divider rule, which equals to 2 volts. We are going to call this voltage V1. Now we set the voltage source equal to 0 by replacing it with a short circuit, and we need to find the voltage V2 that results from the current source. First of all, we need to find the current that's flowing in this resistor, which is I3, using the current divider rule, and this current is 2 amperes. By multiplying 2 amperes by 4 ohms, we get the voltage V2, which is 8 volts. And finally, we obtain the voltage V by adding the two voltages, and this is the final answer. Thank you very much.